In this video, we will learn about the basic concepts of switch. A switch is a layer 2 device, which means it works on the layer 2 of the OSI model. The switch connects the devices in the same network, so all the devices that are connected to the switch, they will belong to the same network. A switch can have multiple interfaces, starting from 8 ports. It can have up to 24 or 48 ports. Right? Each port or each interface of a switch will have its own unique MAC address. As you know that all the network adapter cards, they have their own unique MAC address. So each interface of the switch will have their own unique MAC addresses. All the interfaces of the switch, they'll belong to the same network. By default, switch has one broadcast domain. One broadcast domain. The switch makes the routing decision based on the MAC addresses. So it looks at the MAC address, the destination MAC address field, and makes its decision where to send that packet. It maintains a CAM table which basically keeps the entries about the MAC address along with the physical port details of the switch. So how does the switch learn about MAC addresses? So there are two ways that a switch can learn about the MAC address. One is static. So you can configure a static MAC entry within the switch. You can go to the command line of a switch and create a static mapping that this MAC address A is connected on this particular port. Or switch can dynamically learn the MAC addresses. So which is the most efficient way and most widely used? The dynamic MAC learning. Switch will automatically learn the MAC addresses as the packet moves through the switch. So simplest example is, let's say you have a switch, there are two computers connected, there is a computer A and B. When A needs to send something to B, when this packet goes to the switch learns that I have received a packet on my port 1, physical port 1, from a machine whose MAC address is A. So now it maintains that entry in its CAM table. So now the switch can refer to its CAM table when it needs to find out where is A connected, if someone needs to go to A. So it knows that I need to send this packet out from my port 1. Right? Similar way, when B replies back, so switch learns that there is another device whose MAC address is B, it's connected on my port 2. So then it updates the CAM table with that information. There is one more concept involved with switches, which is ARP, Address Resolution Protocol. So how does ARP work? ARP is a protocol that gets you the MAC address if the IP address of a host is known. For example, let's say you have, again, the same example here, that you have two computers connected through a switch. Let's say the MAC address of computer 1 is A and the MAC address for computer 2 is B, right? They're connected to two ports of the switch. Now, if A needs to send something, maybe you open a command prompt here and type ping and the IP address of B. Let's also assume the IP address is here. So maybe 192.168.1.1 and 192.168.1.2/24. Right? All the interfaces of the switch have to be in the same network. So they're in the same network. So maybe you open a command prompt on computer A and you type ping 192.168.1.2, trying to ping machine B here from A. So when it goes through the layers on the sender side, the packet moves from network layer. On the network layer, it adds source IP, which is 192.168.1.1, destination IP 192.168.1.2. Then the network layer sends it down to the data link layer. Data link layer needs to add source MAC address and destination MAC address. So source MAC address is known because it's the machine who is initiating the packet. So source MAC address is A. Destination MAC address. So we don't know the destination MAC address at this moment. So this computer A, it doesn't know the destination MAC address. So this is where ARP comes into picture. Now, The computer itself will generate another packet, which is known as ARP, and the purpose of this ARP request will be to get the MAC address of 1.2 so that we can complete the packet formation here and send it out. Right. So this process pauses here, and then we initiate a new packet ARP. So the ARP has a source MAC address of this machine A. We'll have destination MAC address. So I'll say destination MAC address that is set to broadcast. So FFF. Right. A MAC address is a 48-bit number. So this 1F is a 4-bit. So we have 16-bit here, 16-bit here, and 16-bit here. So 48-bit. Right. So the ARP will have a source MAC address and destination MAC address set to broadcast. Right. This will also add in the ARP packet. It adds the destination IP address so that when it reaches the destination, it can verify that the packet was destined to me. So in the payload, it adds the IP address 192.168.1.2, and then the ARP goes to the switch. The ARP packet says that my destination MAC address is broadcast. So broadcast means switch will send that packet out from all of its interfaces because it's a broadcast. So that packet goes out everywhere, wherever a device is connected. But only B will accept that because within the in that because in that packet there is an IP address that has to match. So it will only match with the IP address of device B here. When that matches, B replies back. So when B replies, the source MAC address will be B and destination MAC address will be, so whatever the source was in this packet, source MAC address was A. So that will become destination here. It goes to the switch, and now switch knows that there is a device B which is connected to me, and it updates its CAM table. The ARP packet comes back to machine A. Now device A knows the MAC address of destination, which is B, because that information is in the source. So now it continues its packet creation, adds the MAC address here at layer 2, and moves the data down to the physical layer for the binary conversion. Then the packet goes out. So this is how ARP helps. We knew the IP address of a device, and we wanted to figure out what is the MAC address. The ARP helps you to figure out or discover the MAC address if the IP address of a device is known. Let's talk about the basics of VLAN. VLAN is a concept of dividing the broadcast domain of a switch. By default, switch has one broadcast domain, which means if there are multiple devices connected to a switch and there is a packet whose destination MAC address is broadcast, then switch will send it out through all the interfaces, except the interface where the packet came from. Maybe it came from here. So switch will broadcast that, send it out through all of its interfaces, which means switch has one broadcast domain by default. And why do we have that? Because all the interfaces of a switch, they are in one single VLAN, VLAN 1. So that's the default VLAN on a switch. All the interfaces are member of VLAN 1. VLAN is a virtual LAN. So the purpose of VLAN is to divide the broadcast domain on the switch so that you can separate the devices or the machines. Maybe you have two departments and you want to make sure that those devices, they don't talk to each other, but you only have a switch connected. So all those devices are connected through a switch, but now you need, without using a router, you want to isolate them. So you can do that with the help of VLAN. So these devices, let's say devices on the left hand side and there are three computers on the right hand side. Let's give them a name, A, B, C, D, E, F, right? By default, A can talk to B, B can talk to E, C can talk to F, and other way around. Right? But now if we change the VLAN put them in different VLANs, then those machines will not be able to communicate. So you can create VLANs on the switch and make these interfaces A, B, C a member of a different VLAN. By default, they are a member of VLAN 1. So I'll just write the VLAN numbers here. So let's say D, E, and F, they are in a default VLAN 1. Right? And we create a new VLAN on this switch, maybe VLAN 20, and I assign these interfaces to VLAN 20. So now these three machines, they belong to VLAN 20. DEF, they're still member of the default VLAN 1. So now A cannot talk to D, B cannot talk to E, C cannot talk to F because they both are in different VLANs. So different VLANs cannot talk to each other. Now only A, B, C, they can talk to each other. D, E, F can talk to each other. By default, each interface of a switch is configured to be an access port. An access port only allows one single VLAN that it is a member of. Okay. What if we have two switches and they both have VLANs created? So let's say there is one more switch here. This switch also has the VLANs created. So maybe there are a few more devices, G, H, I, and J. Right? And I and J are member of VLAN 1, and G and H, they are member of VLAN 20. Right? These two switches are connected to each other. Now, because G and H, they are also a member of VLAN 20, so which means we need to make sure that ABC can access G and H also, right? And similar way, DEF, they have connectivity with I and J. But in order to do that, those VLANs have to travel from switch 1 to switch 2. And they will be able to travel through this link. But why will this link allow both the VLANs? Because we will do some special configuration on this switch port. So if you need to allow multiple VLANs to travel through one port, that port has to be configured as trunk port. So we'll make this port as trunk port. As soon as you make this as a trunk port, it will allow you to send the traffic for all the VLANs. So VLAN 20 can go out through this port, VLAN 1 can also go out through this port to switch to. So a VLAN breaks the large broadcast domain into smaller. Next concept is STP, Spanning Tree Protocol. Spanning Tree Protocol is a layer 2 protocol. The main purpose of Spanning Tree is to ensure that you have a loop-free network if there are some redundant paths. So it ensures that you have a loop-free network. So we all want redundancy, right? And we want redundancy everywhere. So let's say there are two switches, switch 1 and switch 2. So this is the simplest example. And there is a connectivity between switch 1 and switch 2. On the left hand side, you have some devices connected. On the right hand side also, you have some computers connected here. Right? What if something goes wrong with this cable? Maybe something goes wrong with the port that the cable is connected to. So there is no connectivity then. We want to make sure that there is a redundant path. If something goes wrong with one, then another one can take care of it, take care of the connectivity. So to do that, we have connected two cables here between switch 1 and switch 2. But now this increases the chances of loop at layer 2. So switch 1 might send a packet to switch 2, and switch 2 might send it back through the other link, thinking that the destination is here. Right? Or if there is a broadcast, then that packet will be keep switch 1 spanning tree protocol. The spanning tree protocol ensures that you have a loop-free network if there are redundant paths. So this is to avoid loops in your layer 2 network. Okay. Let's take a simple example. Let's say you have two switches, switch 1 and switch 2. They're connected to each other. There are some devices connected to switch 1, and similarly there are some devices connected to switch 2. Right. Now we want to make sure that there is a redundancy, what if something goes wrong with this cable? So I want to make sure that at least there are two connections between switch 1 and switch 2. If something goes wrong with one, that we have another link which can take care of the traffic. But now adding multiple links here, it can cause loops in the network. What if there is a layer 2 broadcast that comes to switch 1? So if it enters the switch 1 via port 1, then the switch 1 will have to broadcast that out through its all other interfaces. So it will send that packet out via interface 2, it will send it out via interface 3 as well. Right? That packet will enter switch 2 through its interface 1, 2, let's name them 1, 2, 3. So then it enters via interface 1, it's a broadcast, layer 2 broadcast. So what will switch 2 do? Switch 2 will also forward that through all of its interfaces, except from where it came. So switch 2 will send it out via interface 3 and send it out via interface 2 as well. So you see how the same packet is now going back to switch 1 because there are redundant paths. So this is how we will create loops. The spanning tree allows you to avoid loops. So when you enable spanning tree on your switches, they start talking to each other. They send BPDUs, which is known as Bridge Protocol Data Unit. So these BPDUs, they will have the information from switch 1 and share it with switch 2. So when you enable spanning tree protocol in a network, in a layer 2 network on your switches, so they elect a root switch and start sending BPDUs, Bridge Protocol Data Unit, to each other so they can communicate and share information. Wherever there are redundant paths in the network, the switches will automatically take care of the redundant links and move them to blocked state. So this link, one of the link will be logically blocked. And if something goes wrong with other path, then the switch will automatically move that port into forwarding. So this port will go into forwarding mode and it will start catering the traffic.